D4. Root cause finding. These are the high-level general steps for root cause analysis. First, perform the initial data collection and analysis. From here, brainstorm to identify all the potential causes. For complex technical issues, such as test or design issue, we might need to invite new members. If this is the case, the team is actually back to reforming stage. That is, we are back to D1. Please do not assume the new member understands the background of the issue. The new member just joined the team. He or she did not participate in earlier discussions. 8D team might need to spend some time to brief and bring the new member up to speed. Every team member can freely and openly brainstorm the potential root causes based on their opinions. But the team could not afford to study each of these potential root cause if it is the actual root cause. In real world, 8D team has resource constraint. Together with the initial collected data, or facts, team needs to select the most likely root causes. Then, collect more data, or carrying out the experiments, to verify and confirm it could be the likely causes. Once the likely root cause is verified, we need to reperform the risk assessment, based on the latest findings. Few questions we should ask here include: is the containment action defined in D3 still appropriate? Could it be enhanced? Do we need to redefine screening method? Do we need to redefine the containment boundary? While doing this, we are actually back to D3. Containment action. Let's zoom into the very first step of root cause finding: initial analysis and data collection. Review existing data, whatever readily available, for the clue of potential causes. From the serial numbers of affected products, trace the manufacturing history. Did the product go through any rework? Any abnormal long idle time at certain process? Any change during the manufacturing period, in term of man, machine, method, material, metrology, environment? Lastly, we could analyze the trend of defect rate. Is it gradual issue, continuous, abrupt, or periodic issue? Has the problem occurred previously? Brainstorming approach is used to identify all the potential root causes. One of the most common brainstorming tools is fishbone diagram, also known as cause and effect diagram. There are two types of root causes needed to be brainstormed. First, root causes for occurrence. What caused the defect was built. Second, root causes for escape. Why the defect was not detected, and escape to following process or customer. Some companies, they design their 8D form in such a way that there are two fishes kissing each other in D4 column. One fishbone was used for root cause for occurrence, while the other used to brainstorm root cause for escape. The process of brainstorming for root cause is also known as generating root cause hypotheses. Just for examples, the typical potential causes are torque too high or too low, operator pressed too hard, cure time too short or too long, tool worn, speed not constant, inadequate or no lubricant, skip process, hardware failure. There may be more than one root cause for a symptom. Sometimes, the root cause might be due to the interaction of two factors. For example, interaction of design and material, that is, design marginality issue. Interaction issue definitely will add the complexity into the root cause finding, especially for junior engineers. There are two major analysis approaches in finding root causes. Failure analysis, data crunching, or data analysis. Whenever possible, we should use these two approaches in parallel. There are two types of failure analysis, that is, electrical failure analysis, and mechanical failure analysis. Electrical failure analysis is through the understanding of circuit schematic, while mechanical failure analysis is through dimension-tolerant analysis, cross-section, Dien-Pry technique, etc. There are many statistical tools available for data analysis. Anyhow, this is beyond the scope of this training. When there is opportunity, I will develop a training video for this. Scatter diagram is one of the common tools used to study the correlation of two variables. Or, in more layman, to study the relationship between two variables. For example, say your customer reported broken screw head issue. You suspect this is due to smaller screw diameter. Hence, you perform an experiment to study the correlation between the screw diameter and the pulling strength to break the screw head. We can plot the collected data, diameter versus pulling strength, on horizontal and vertical axis respectively. This scatter diagram will show the relationship between the pulling strength and diameter. We can even use this diagram to determine what is the minimum diameter, which will ensure meeting minimum pulling strength. Another common statistical tool is trend chart or control chart. One of the powerful techniques in data analysis is called stratification and commonality analysis. Let's spend some time to discuss stratification and commonality analysis. What is stratification analysis? Stratification analysis is a technique of analyzing data, based on separating the data elements into several groups with similar characteristics. While commonality analysis is a technique of analyzing data, to identify the commonality, or pattern, in terms of man, machine, method, material, metrology, environment, or time. Product is an output of manufacturing process. While the inputs of manufacturing process are material, man, or operator, machine, method, and environment. In other words, the quality of the product, which is the output of manufacturing process, is influenced by these 4M+E. To enable the commonality analysis, our next step is to collect the corresponding data for each of these 4M+E. The step is: find out the serial numbers of the defective products reported by customer. Then, use the shop floor control system to trace back the historical data. For example, trace back the lot number or date code of material used to build the defective product. For man, trace the operator who built the product. Identify the machine number or line used to build the affected products. Lastly, obtain the time when the products were built. Based on this time, we can trace back further on which method was used to build the product, and what is the temperature and humidity at that time. Generally, we can find out the temperature and humidity info from the facility department. While for method, we can trace back to the standard operating procedure, which was effective at that time. Most of the cases, material, man, and machine, are critical data to trace. Unless you have reason to believe so, otherwise, you might not need to trace to the method used. Same also, just in case your product or process is very sensitive to environment, otherwise, it is not necessary to trace back to temperature and humidity. This is a typical format for collecting traceability data. Each row represents a product with reported issue. If you want, we can add another column to indicate the serial number of the reported product. First two columns to indicate the reported defect mode and affected product respectively. The next three columns are the traceability data of machine, time, and operator for first process. The subsequent three columns are traceability data of machine, time, and operator for second process. We will repeat tracing these machine, time, and operator info for all the relevant processes. Finally, we will trace the materials used on the reported products. Say, this is the traceability data for 6 broken bulbs, which reported by your customer. Do you see any commonality among the data? Suggest you pause here for a while, and see if you able to see any pattern in the data. So, what is your guess? Right. I will guess lot number 0011 for material O might be the suspected root cause. This is the commonality, or pattern we can see from the data. Anyway, you might ask. The last bulb used lot 0012 for material A, instead of suspected 0011. Why it was broken too? We have to understand, the actual world is not perfect. Even we only use a so-called good material, we still tend to see some failures from time to time. We see these as random failures. The last bulb might be a random failure, part of the normal fallout. This kind of data point might mask up our data and cause some confusion in finding the commonality, especially for junior engineers. Commonality analysis is one of the powerful techniques to identify potential root cause. Here are some tips to ensure the efficiency and effectiveness of the root cause finding. Customer may need to be involved into root cause analysis to speed up the process. For example, to loan customer system, especially for those failures not able to duplicate with internal tester. Request customer to ship more defective samples, plus collaterals, if applicable. This is to enable concurrent failure analysis could be carried out. We might need to spare some extra defective samples, by knowing some failure analysis activities are destructive. 8D team should clearly define the objective of experiment, or DOE plan. Team needs to anticipate all the possible outcomes and clearly predefine how to interpret the result for each of the POS from the DOE result. Escalate to management for support, if needed, for example, while we need machine availability to conduct experiment. Or, when we need budget to support the cost of experiment. There are situations, 8D team does not able to get the support from relevant content expert. Sometimes the content experts are defensive. They might make a position that, I will not support or do anything until you prove I am wrong. To prevent this, company needs to set a policy that, relevant content expert is required to support the investigation, as soon as the hypothesis is established, even the strong evidence was still not available at that time. That means, we want content expert to play more active role in investigation, instead of passive role. If there are 2 or more suspected root causes, and resolution owners are from different parties, we shall investigate all the potential causes in parallel to expedite a solution. If we investigate the root cause in serial, one by one, there are chance the first hypothesis is not the actual root cause. This will force us to investigate the second root cause. Anyway, by that time, we already lost out the time spent in first root cause analysis. Hence, as long as resource permit, we should do parallel investigations. For complex issue, especially design related, suggest to form separate technical team to work on root cause offline to speed up the root cause identification process. The reason for forming sub-team is to avoid the detailed discussion in the main 8D team meeting, which might not the interest of all parties. Forming of sub-team will prevent dragging the meeting into long hours, and make the team more effective and efficient. We should further enhance is versus is not table, introduced in D2, to find the path for the root cause identification. Another good approach is Ask 5 Whys. 5 Whys is a simple technique to probe for the root cause by repeating asking the question why. Though we name this approach 5 Whys, it does not necessarily mean we have to ask exactly 5 whys. Sometimes we have to ask few more whys than 5 times to reach the root of the problem. While there are times, we able to reach this point by asking less than 5 whys. Let's have an example. Dented mark is observed on the phone casing. The answer for first Y, dented mark was induced by tester probe. Second Y, operator did not place the unit properly into test fixture. Third Y, difficulty in placing the unit properly. The fourth Y, difficult to place properly, because the dimension of the unit was shifted. The fifth Y, the dimension shifted due to the flaw in new mold fabrication. Let's have second example. Electrical failures escape to customer. First Y escapee. Wrong program was used. Why wrong program was used? Operator keyed in the wrong part number while pulling out the program. Why need to key in part number? Shouldn't the test program to be auto-loaded based on scanned barcode? This question probes further investigation, and traceability record found that the escapees were tested through offline testing at that time. But why and what trigger for offline testing? Investigation found that the shop floor control system defined the route to skip auto testing for rework units. But why defining such a way? Due to not enough online test capacity? Due to high false call rate? Where production has to use offline testing as additional test capacity. This third example, the vehicle would not able be started, is a case study, shared by Wikipedia. First Y, the battery is dead. Second Y, the alternator is not functioning. Third Y, the alternator belt has broken. Fourth Y, the alternator belt was well beyond its useful service life and not replaced. Fifth Y, the vehicle was not maintained according to the recommended service schedule. One of my favorite tools in D4, root cause finding, is hypothesis table. Let's use a case study to illustrate the application. Customer reported 11 out of 2,000 PCBAs with poor soldering quality on specific component. While soldering the component's legs on PCB solder pad, or solder land, there are two main interfaces. First is interface between leg and paste. Second interface is between paste and PCB pad. Firstly, we list down all the root cause hypotheses in the first column of the hypothesis table. For example, the poor soldering might be due to low reflow temperature. Or, it could be due to poor rework, or, insufficient solder was printed. Another potential root cause is, the legs of component was contaminated, and prevented the good soldering. Once listed down all the root cause hypotheses, we will fill up the supporting facts, and contradicting facts, for each of the hypotheses. Fill up these horizontally, row by row. When applicable, document down the next step too. For hypothesis of reflow temperature too low, the examples of the supporting evidence are: observed poor solder wetting, solder not able to wick up the side wall of leg to form ideal fillet, tarnish color at solder joint area, joint is not fully formed. Anyhow, your failure analysis team also observed proper IMC, intermetallic compound, formed at interface between paste and PCB pad. Non-wetting only observed at interface between paste and leg. If the problem is due to low reflow temperature, generally, we should observe the soldering issue at both interfaces. To confirm this, the proposed next step is to cross-section the adjacent similar components. If the issue is due to low reflow temperature, then we should observe the similar poor soldering symptom on these adjacent components too. Let's move to second hypothesis, poor rework. The supporting fact is: manufacturing record for certain returned units shows the specific component was reworked. Anyhow, not all the reported units were reworked on the specific component. This becomes the contradicting fact. While for third hypothesis, not enough solder. The supporting and contradicting facts could be same as low reflow temperature. On top of that, the additional contradicting fact is that, did not observe insufficient solder from returned units. To buy more confidence in ruling out this hypothesis, we can trace back the SPC monitoring data, to confirm the solder paste height or volume, is sufficient. The last hypothesis here is, component contaminated. The supporting facts are same as low reflow temperature. To confirm if the component contaminated, we can perform semi-DX analysis. The beauty of the hypothesis table is, it will visualize all the facts on a single table. By documenting down all the facts, which provided by team member, is one of the ways to acknowledge the contribution of team members, and it will prevent future dispute. Sometimes, we will come across a team member, repeating the same facts, with the intention to influencing others that, the root cause is from other area, and not from area owned by him. For that case, we can show him, or her, the hypothesis table. And politely tell him, or her that, we have already documented his, or her, input. And we should move to next discussion. This will prevent speak louder member nominate and dragging the whole meeting. If not the worst, mislead the team to wrong root cause. To enhance your understanding of this critical tool, let's have another case study. This time, we observed functionality failures due to microcrack at various components. The potential root cause hypotheses are: reflow induced, that is, the temperature too high. Incoming material. SMT machine induced, and customer induced. The supporting fact for reflow induced is, cracks only happened on small components, which with lower thermal mass. The temperature of components with lower thermal mass, will increase faster while going through the reflow. The high temperature might be potential cause for the crack. Here, we do not have contradicting fact. The next step is, to trace back the record of the reflow profile, which was taken during that time period. We rule out the hypothesis of incoming material, because there are total 3 different components affected, and from 2 different suppliers. From probability point of view, it is unlikely that coincidentally all the 3 components from 2 different suppliers having quality issue at the same time. Furthermore, some other products were built with same reels of components too, but found no issue. For SMT machine-induced hypothesis, we do not have any supporting, nor contradicting fact yet at this moment. We assign an action to SMT engineer to figure out if all the affected components were placed by same SMT nozzle. If yes, then the issue might be induced by improper installation, or setting of nozzle. We also rule out the hypothesis of customer-induced. This is because we found one PCBA, still yet shipped to customer, exhibiting same symptom. Hypothesis table is a life document. From time to time, we will update it with latest information. In the end of this exercise, it will enable us to select the most likely causes. If we observe correlation of 2 events, it does not necessarily mean that one is cause of another. For example, number of TV sets sold in a year, is correlated with the number of available chickens in a specific country. Though there is correlation, we should not conclude that the number of TV sets sold is caused by the number of chickens. Chicken would not buy TV. They are not the cause. The reason for correlation is because there is another hidden factor, which correlate with these 2 numbers, that is, population. Jumping from correlation to conclusion, is one of the common pitfalls. Common mistake done by inexperienced engineers. Let's have a case study to explain this. Say customer returned 5 PCBAs due to no display. Through X-ray inspection, initial failure analysis found 5 out of 5 PCBA with solder bridging at BGA component. In general, whenever observing solder bridging issue, engineer will conclude this is SMT process related issue, instead of design, or other issue. Further failure analysis, observed 3 out of 5 BGAs have burnt mark, indicating the components were overheated. So, a question to ourselves is overheat caused bridging? Or bridging caused overheat? For this case, maybe it is true that the SMT process issue is the root cause which lead to no display issue. And due to the shot between the solder balls, cause the component overheated and burnt. It is also possible a design issue, which lead to component overheated, melted the solder balls and caused the solder bridging. We do not know which is the actual root cause. We need more data point, we need further analysis. Anyhow, the takeaway point here is, do not jump directly to the conclusion based on certain observation. The observation might just a symptom, but not the root cause. Once selected the likely cause, next is to verify and confirm it. The end in mind is to duplicate the failure, based on the root cause hypothesis. There are times we need to run experiment. For this case, we need to design an experiment based on the objective. Determine the sample size to be run in the experiment. This is especially important, for issue with low failure rate. Small sample size might not enough to surface up issue and underestimate the issue. Finally, collect and analyze the data. Perform FMEA, if necessary, to ensure the DOE will not induce any defect. As mentioned earlier, once the root cause is identified, with better understanding of the issue, we might need to reperform the risk assessment and decide if we should back to D3 to redefine the containment plan. If you see value in this video, please click on the thumb up and share. This definitely will motivate me to make more quality video related to this. Please click on subscribe too, this will ensure you would not miss any subsequent videos. Before we end the session, let's close our eyes, observe a moment of silence, pray with your own respective religion. May the community full of peace. And may the world free from disasters. Looking forward to see you in next video. Thank you.